Hello and welcome back to my review of Advent of Code 2024 solutions in ARM assembly for the Game Boy Advance. We're up to day 5 of 10. So let's see what our problem today is. What we've got is a print queue, and our input is a list of page ordering rules and pages to produce in each update. So lists of pages to produce in each update. Right, the page ordering rules have 2 per line. For example, 47 pipe 53 means that if the update includes both page number 47 and 53, then 47 must be printed at some point before number 53. Doesn't have to be immediately before. If the page numbers aren't in the update, it doesn't matter. We just ignore the rule. Right, the second section is the list of pages in each update, and that's fine. Right, it's just a list of page numbers. So for part 1, what we want to do is check which ones are already in the right order. Right, for example, this first one here, 75, 47, 61, 53, 29. 75 is in the correct place because we have 75, 49, so 47 has to be after 75, 61 has to be after it, 53 has to be after it, 49 has to be after it, 29 has to be after it. Right, 47 is correct because of 75, 47, but then 47, 61, 47, 53, 47, 29. 61 is in the right place because 75, 61, 47, 61, and then 61, 53, 61, 29. 53 is in the right place because we have 53, 29, and all the other ones before it. Actually, I don't know if there's any others that start with 50. Yeah, there's only that one. No, there's one over down here as well. And then you have 29 is the last page. Doesn't matter, it has a rule, but 13 isn't in the list, isn't in the order, the update here, so it gets ignored. That's how it works, right? Effectively, what we're doing is sorting, but instead of sorting in like ascending or descending order, we're sorting to these rules. So I want to keep that in mind. So first we're checking, and we have to add up the middle page number from the correctly ordered updates, right? The middle page number, we have to add all the middle numbers together. So that already means that all these updates are going to be an odd length, right? The even number of length was the middle number. Right? They all have to be odd number lengths. And obviously for part 2, we want to correct the orders. We want to sort them correctly, right? And then only looking at the incorrectly ordered ones, we want to add up their middle page numbers, and that's the part for us for part 2. So we should be looking for 6498 and 5017. Alright, let's look at the code, shall we? Let's bring that back. So, what have we got here today? We've got our results, of course, ASCII num returns. We have to read numbers in. Of course, we've got a result buff and rule array. So I believe what I'm doing here is that I do bring in all the rules into a big array, so I can read through them for each result thing, and then each result gets checked one by one. So we go on here. We've got our solve day, the start and end of the input. R10 is going to be my mode. mode 0, we're storing the rules. Number 1, we're processing the results, and then we end. We clear out ASCII num. Right, we clear out ASCII num there, and R7 hold first number for rule. Now, I'm not sure why I'm actually doing that, but who cares? Anyway, so we've got our compare to see when we're finished the input. So we read in a byte. We check if we are in a line break, and it'll go to check double. Then we can, depending on if we're in mode 0 or mode 1, we either read rules or read results. Right, and then we increment offset. Right. So, and I've got to have two different ones here, because when I'm reading the rules, comp7c is a pipe, right? So whenever I see a pipe, I have to convert ASCII, and if it's not a pipe, then I read a number. This is one of these cases where, because I'm branching, I actually have to do two comparisons, right? Because I'm branching and linking. Suppose, well, what is, I suppose what I could have done, I'll convert ASCII down here. No, because I'm doing this, backing up all the registers. I guess ideally what it would have been better to do is have it just branch to convert ASCII or branch to read num, and then from those come back to inc offset. But it's okay, that's fine. Anyway, so those are basically the same, except that read results is looking for a comma, 2c is a comma, and read rules is looking for a pipe. Read num just takes in the number, converts it to a binary format, BCD, stores it in ASCII num for conversion later. Inc offset adds 1 to R8 and jumps back to read loop. So check double, right? Whenever I hit a line break, go into check double, convert the ASCII, add 1 to the read pointer, and load it in. If it's I'm looking for the separator between the rules and the results. Let's bring back the browser for a second, right? I'm looking for this separator here. So when I hit a line break, OA, I'm checking to see if the next byte, so I hit a line break on then after this 3, I hit an OA there, and then there's another OA in between these two lines. So if I've got two OAs in a row, I'm now changing into, if it is equal, I'm adding 1 to R10, and if it's equal, we go to inc offset. Then I compare R10 to 0, and if it's still 0, we go back to read loop. Right. So I only want to increment the offset. I don't want to branch to increment offset after adding 1 to R8, unless it's actually the gap between the two. Alright. So read rules, read results. Where are we? Ah, right. So if it's not 0, right, if it's 1, then it will skip out of this one here. It'll go into the evaluations, the evaluation, evaluating the results, right? So this here, and then it will clear the result buffer when it comes back from eval result, and then branch back to read loop. So when it's reading the results and it hits an OA, it will come through this check double. It won't be a double, right? But R10 will be 1, and so it will go into this. Now actually at the end of the input there's usually an extra line break on the end. So it will actually come into this and become a 2. R10 should become 2. But that's not really important because it would come out of that and like immediately hit this and go, oh, I'm at the end. But anyway. Alright, so convert ASCII, I think we've been through this a number of times already. But we have a check in here. Right, well, go through it again. So R0 will be our result, the binary result, R3 our multiplier, R4 our 10 value for increasing the multiplier. We load in each value from ASCII num. Right, we load in each value, multiply it by the multiplier, we add it to the result, register 0, we multiply the multiplier by 10 for the next digit, and then we store that back into the multiplier, and we subtract 1 from the length, from the pointer for ASCII num, and then do the tens column, right? Then we reset the ASCII pointer, the length of ASCII num, that will be 0. The value of R5 will be 0, and so we'll store that 0 into that pointer. And then whether it's 10, if it's result, probably insert result. Okay. So depending on, I think what I ended up doing, yeah, I think so. I think what I ended up doing was something about the because there's so many rules, I couldn't check every rule. I couldn't just do every rule for every number. I actually had to be a little bit smarter and store the rules in a smarter way. I'm trying to remember exactly how I did it. We may find out soon. So if the number is not 0, then we store an ints result. We jump to ints result. If R10 is 0, then we check R7, and if it's equal, then we branch to set left rule. If it's not equal to 0, then we branch and link to ints rule, which will insert rule, and that will come back here, and then with 0 R7 again, and then then move, then jump to end conf ASCII. Right. And so we have here if if R7 was 0, then we put the value of we put the value of R0 into R7, and then we go to the end of revert ASCII. Right, so that ints rule is going to take the contents of R7 and R0 and it's going to do something with them. We'll find out soon. And then we have the ints rule here, int result here, which is going to load the result buffer. It's going to take the pointer, add 1 to it, store R0 into it, and then store that new pointer value. And in conf asc is just goes back. It restores. It leaves. It doesn't return. What is that? It doesn't back up and restore the value, the contents of R7. R7 returns from it. And now let's see. Let's have a look at ints rule here. So, what do? I load. So I move 256 into R11. Now I think if I remember correctly, each rule had like 240 pairs. So say a rule started with 75. Actually, we've got over here, like, right in the real input, you might have on the left a value like 75, and that would be paired with 240 other numbers. Right, there'd be 240 rules starting with 75 on the left. I think that was about how it was. Right, let's get rid of this window now. Don't need it. And so we're starting off with a fairly big number, right? 256 is in R11. So I load the location of rule array, and then I compare. If it's 0, then we branch equal to new left. Right, this is a new left side rule. Right. Otherwise, we go looking for the rule. We're looking for a left side rule, right? So we iterate through the length of the rule array, looking to see if we find if there's the value of R7 is in there. Right. If we don't find anything, then we'll fall into new left. But if we do find something, we'll go to add left. If we fall into new left, then we load up that pointer again. We add 1 to it. We store it, the left side into it. We store. Okay, right. I think I remember what I was doing now. We store the value of R7 into there, and we store the pointer in there. Then we take that position, right? So it's like it's index 1. And we multiply that by 256. And then we add. What do we add to it? You get that in R3. Then we add the index to that. and that's where we're going to insert this this rule. Wait a second. I think onto it. Yeah. I'm trying to work this out in my head. It's a very bad thing to do, trying to work things out in my head. So I multiply it and then I add it to, because R3 is pointing to rule array, right? It's pointing to rule array. So by adding R3 to it, I'm basically going like the index of this left side, say index 1, multiplied by 256 plus the offset, the memory offset of rule array. And then that's going to be the index, the position where this counter is going to be stored. This pointer is going to be stored. I think you could call it a counter. It's going to be stored for the values, number of values in this sub array, right? So I guess in a way this is kind of like a hash map in some ways. I kind of want to like try to illustrate this. Let's see if I can do something of an illustration. Don't want what? I know why I did that. Let's see. Can I do something of an illustration? Let's do. Actually, let's go back here again. Let's see if I can add another application to this, shall we? Is there another window? I'll try and bonk. That's there. Okay, so what am I doing here? So let's say I'm going to put this thing in here. Let's get some size up on here. Let's just say, right, rule. We've got our right, our memory should be that there. Right, we've got our memory, just our memory going down like this. Right direction, wrong direction. Doing it the wrong way. We've got our memory, right, going down here, and we've got rule array starting at some point in memory, right here, right, and our first position here is the pointer, right, how many values are in rule array, right, and we might have like, let's say we've got 5 values, right, the first one is 20, we got 10, 15, 62, 63, whatever, 24. Okay, right, we've got these 5 values that are in our rule array. Right, so this is going to go, alright, so say we've got rule 20, right, is at index, let's get some different colors here, is at index 1, 2, 3, 4, 5. Okay, so for these are the left hand side of the rules. So to find all the right hand side values, we take this index 1, right? The index 1. Let's go the other way like this. Yeah. Right? We take the index 1, we multiply it by 256. Right? And we add that on to the location that rule array is at in memory. Right? So we get an offset which will point down, I mean we'll just say it's at 18. Now I've got to do hex conversions. That's joyous, isn't it? Okay, it'll be 10, 118, plus this index here, plus 1. Right, so it's going to be 010 plus 018 plus 1 will be where the pointer for the number of values in for the 20 ones will be stored. Right, come down here somewhere. Right. Then the next number, number 2, would be, because we take 2 and we multiply 2 by 256, we'd end up with 0200 plus 18 plus 2. Plus 2? I think it might be plus, no, it's plus 1 because it's adding plus 1 to each one of them rather than the index, right? I think it's adding plus 1. Oh, there's no plus 1 in there. No, wait, there is. Yes, there is. Oh no, that plus 1 is where I'm storing the thing. Wait, there's no plus 1 on this. Okay, that's fine. This is fine. Plus 1 is where the actual value gets stored on the right side when a new left side is made. Right. So I can get rid of that this plus 1 over here. Doesn't matter. No, it never existed. Right. And so that way, this way, right, I'm calculating, like just using a simple math, right, I can work out where in memory each of these sets, lists of paired numbers is going to be without actually having to store them all, right? I store I store the left side once, and then I store all the right sides that are associated with that left side in a list, in a point of memory that I just calculate. Right. Right. And each of these will just point down somewhere further and further, further and further in memory. Something like that. Alright, now that terrible illustration's gone, let's go back. Right. So, and then we add 1, or we put 1 into our offset from that pointer position. We store the right side, and we store that offset, and then we exit the insert rule. Right. That's if there's a new left rule. If we're adding to the left, right, then we do that multiplication again. We add the rule array position to it, We load from R2. We load from there, from R3, that position in memory. The offset that's currently there, right? How many numbers have been stored in memory, in that memory slot, in that list. We add one to it. We store the new right hand side onto the end of that list, and then we put that offset back and we exit the insert rule. So I've inserted that rule, or I've inserted the rules, right? I think so. We're basically done there. So eval result. So what I'm doing here is that I've got move R10. We're going to use register 10. It's going to store the number of corrections done, right? Because for part 1, any results that are already correct, they're already in the correct order, are for silver. Any that need corrections will be gold. So I'm just doing them both together, right? R11 is that 256 value again, and we're going to branch into run sort, right? Because we're sorting the list by those rules, right? We're sorting those numbers by the rules. And then when we come out, we look at wait a second, we run sort, we load result buff. Right, so when we come out, we want to get the middle number, and so effectively what I'm doing is a simple division by 2 by logically shifting it right. It works because I don't need a remainder, so we can lose, you know, if we discard a bit, it doesn't matter. We're effectively rounding down when we do this result, right? So we load that result buffer, the length of the result buffer. I add 1 to it. Some reason. Add 1 to it, and then I logically shift it right to get the thing. I think I need to make it an even number. Wait a second. Because if it's 5 in length, right. Okay, right. If it's 5 in length, it would be like the last 3 digits would be 101. Now if I just shifted that left by 1, then I'd get 2 as my result, which would be wrong. But if I add 1 to it, it'll become 110. And if I shift that left, then I get the result 3, which is correct. So I can only do this because I know that they are odd numbers. I can add 1 and then shift it left by 1, and I'll get the middle number. I'll get the address of the middle number. Right. So if it was 7, add +1, I'll get 8. And then if I have 8 in binary, I'll logically shift it left, or logically shift right by 1 space. I'll have 4 as the result, which will be the middle number of 7, of a 7 length result list, right? And then what I do is I compare, I load the, actually, I mean, I could have done the compare and then done LDR EQ res1 result address and LDR not equal any res2. But anyway, so I load the address of the result 1 address by default, and then if it's if R10 is not equal to 1, not equal to 0, then I load the address, the result 2 address, and then I'm updating that with the middle number that I loaded out of, yeah, adding that to it and then storing it back in there. Okay, so run sort, mostly copied from day 1, but there's a bit more going on because I have to, rather than just checking greater than, I'm actually checking like ordering. Effectively, all you have to do is flip the numbers around if they are not in the correct order, right? If I'm comparing these two numbers and I have a rule which says that, you know, they should be the other way around, then I just move them the other way around. That's fine. So we'll load in our result buff, right? The length of it. I put 2 into R8. I move 1 into R6. These are going to be kind of my offsets of where I'm going to be loading out of, like along the length. I load from position 2, right? R8 position 2, R0, and then we branch into subsort, right? And so we load into here. Wait, subsort, where are we? Here, subsort starts off here, right? Back up, deleting things, back up those registers. We load from the position of R6, which is starts off at 1, but it will be counted up. Interesting. Yeah. But it'll be counting up. We go into our rule array, right? We look for a valid rule comparing with R0. Right, this will be the left hand side. And I think it's the left hand side. It should be left hand side, yeah. What was R0 again? Okay, yeah. Because remember, R8 starts at 2. So we're looking we're looking to the, like, R0 holds a value that's to the right of the value that will be in R1. Right? R0 starts at position 2. R1 starts at position 1. So R0, we're comparing to R0 here, is the left hand side rule. We load the left hand side rule if we find it. If we otherwise branch to the next rule. Right. Otherwise we branch to the next rule, which will branch that and go back up to loop rules. Yep. If we once we find the rule, we'll multiply by 2556, add on that rule array offset, and load in that, and then we look we loop through the right hand side, that list of right hand side numbers, right, and compare that with R1. And if they are equal, so R0 holds the left hand side, R1 holds the right hand side, then we swap around R0 and R1 in the result array. And we swap, well, we put R1 into R0 because they are swap positions. The same way we did the bubble sort, really. We add 1 to R10 to say that we've done a correction. and it would branch to our next res value. Right, we add 1 to R6, and we compare R5, R8 to R6. If they're equal, then we exit sub. Right. Otherwise, we branch back to sort loop. Next write increments or subtracts 1 from R4. Right. So once we're in this loop right, if we finish, because we're reusing R4, we used R4 to begin with on loop rules, and then we started reusing it again, right, over here, as the offset for the right hand side. So once it's done, we go to next res val, and I have to go down here and increment R6, which will take us all the way back up here, which will initialize R4 again as the offset rule array, rather the left hand side rather than the right hand side. Yeah. So it's doing the same bubble sorting that we did in day one, except it's using these rules as comparisons, not the size, not the comparable size of their values, right? And so it just moves them around until it gets to the end, and then we exit this. It just moves it around until R6 and R6 and R8 are equal. Then we'll add 1 to R8, and then once we get to R7, then we are at the end. Right, once R8 is equal to R7, we're finished. Oh no, once, because I've got less than or equal to, right? BLE, less than or equal to. Once it's gone higher than R7, then we are finished. Sorting. And it goes back, and then it will add it to, it will work out which number is the middle, and it will add to the results. Right. And that's all the code for today. Alright, let's have a look at it running, shall we? Might be a nice day to look at the memory as well. Again. Okay, so we'll start this up and go. And it's done. Alright, that was the correct result. So that's all good. Alright, let's have a look at our memory. Now, one thing you'll immediately notice, I'll bring this up. Okay. I think here is our ASCII numbers here. Here's our result array. Right. Or at least. Oh no, I think that's right. The result array. Yep. The results still going to update every frame. And here are our this is our list of left-hand side numbers. This is out with 49 left-hand side numbers. And there are actually far less numbers in each pairs than there was before. That's right, 24. There's 24 numbers for each. So yeah, way too much space. Oh, that's alright. That's fine. And you can see here we have 24 numbers for each. Yeah, so for 85 there were 24 numbers paired with it. Then you have the next one here, next one here, next one here. Right. So I could have used a much smaller value, and it just keeps going on and on and on down. Instead of 256, I could have done something. Not 24. That would have been too tight. First thing I have to get past this block. So down here somewhere would be ideal. Something like 64 would have been adequate instead. Anyway, so let's run this one more time. We'll see up here. Well, it'll be going too fast to see anything probably, but let's go. Yep, going wild. There we go. And that's our result. Alright, so that was day number 5. A bit more interesting. I think the first thing I tried to do was just storing every rule and then checking, iterating through every rule for every comparison, and it was it was just forever. It was going to take forever. Yeah. But this made it a little bit easier. Alright, okay, so I hope to see you again for day 6. And until then.